Good afternoon, General Chemistry. We're picking up with our notes. This is going to be Chapter 14, Part 3. So we've talked about the three gas laws, Boyle's, Charles, and Gay-Lussac's. So let's just do a little quick review together. So here's this picture. We show this would be a piston, so we have some gas here pushing on the gas, and this would be a pressure gauge. So high pressure, low volume. Then if we make the pressure lower, low pressure, high volume, that means the volume gets bigger. So as the pressure goes up, the volume goes down, and as the pressure goes down, the volume goes up. Which law is this? So you should have answered your question, and it's Boyle's law. Pressure-volume relationship is Boyle's law, and it is an indirect relationship. As one goes up, the other goes down. All right, let's try another one. We have a balloon filled with air. Here's it at room temperature. If we heat it up, it gets bigger. If we cool it down, it gets smaller. So as temperature increases, volume increases. As temperature decreases, volume decreases. What gas law is this volume-temperature relationship? It's Charles' law. It's a direct relationship. As temp increases, so does volume. One last one here. So again, now we have a container, and it's kept at a constant volume. There's gas particles in here. So if we, right now, you can see the pressure's at 2, and here, and if we increase the temperature, what happens to the pressure? We see that it doubles. So as pressure increases, so does temperature. So what gas law is that? As pressure increases, so does temperature. In other words, as temperature increases, so does pressure, because these gas molecules are moving around. So what gas law? The answer is Gay-Lussac's law. We know that's a direct relationship between pressure and temperature. All right, so now that we have those three main laws under our belt, we're going to combine them to make the combination gas law. So this expresses the relationship between pressure, volume, and temperature, all those three variables that we've been learning about, for a fixed amount of gas. So here's our equation. P1 over V1 equals, over T2 equals P2 times V2 over T2. You'll notice it's literally just a combination of all the gas laws put together. If we take away T2, or the T's, we'd be left with Boyle's. If we were to take away the P's, we'd be left with Charles, and if we take away the V, the V, we'd be left with Gay-Lussac's. So a couple other ideas, and we'll do some equations with the combined gas law. The partial pressure equation, pressure of an individual gas in a mixture. So there's an equation for this. When gases are mixed, the pressure that each gas exerts is independent of the other gases. So that just means how much force each individual gas exerts, and that led Dalton, to come up with this rule of partial pressure. And all it means is that if we want to know the pressure of a total amount of gas, we have to add up each gas's pressure individually. And again, this follows the ideas of the kinetic molecular theory. Since gas particles move independently of one another, gas pressure is the result of collisions these particles have with the container. And then we need to talk about Avogadro again. If you remember back from a few chapters ago, we've talked about Avogadro's number, the mole. So the mole comes into play when we talk about gas as well. So Avogadro stated that equal numbers of gases at the same temperature and pressure have the same number of molecules. Okay, so here's a step through his principles. If equal volumes of gas have equal number of particles or molecules, okay, and 1 mole of a gas contains 6.02 times 10 to the 23rd particles, then for any gas at STP, and STP means standard temperature and pressure. So there's a standard temperature and pressure he measured things at. If there is 1 mole of particles, it must be a constant volume. Okay, so that leads to this assumption that if we have 1 mole of gas and it's at STP, standard temperature and pressure, which we're going to assume they are, we'd have 22.4 liters. So we can know the volume of a gas, okay, if we know the moles and the standard temperature and pressure. And that'll come into play here with the ideal gas law. So this is the last law we need to learn about gases. So remember, an ideal gas is one that perfectly follows the kinetic molecular theory that I had you write down at the beginning. Using the gas laws and Avogadro's principle, we can see the relationship between pressure, volume, temperature, and moles. So far we've talked about pressure, temperature, pressure, volume, and temperature, but not moles. How much is there? So here's the gas law. Units are very important for this law. So we have pressure times volume is equal to the number of moles, that's what N stands for, and this is a constant, and temperature. So the constant, this is the equal to, it's equal to 8.31 kilopascals times liters divided by moles and Kelvin. It's derived from all these places. So jot this down, and we're going to do an example problem using this PV nRT. A lot of times we say perv nert to help us remember this equation, PV nRT. All right, so let's do this equation together. Again, feel free to pause or go back if I'm going too fast. Let me get my pointer. Okay, if a balloon full of gas has a volume, so here's our volume of 0.351 liters, a pressure, here's our pressure of 101 kilopascals, which is a unit of pressure, and a temperature of 297 Kelvin, how many moles of gas are present? Okay, and moles again is N. All right, so we have pressure, we have volume, we have moles. Oh, we don't, what are we missing? What do they want? Oh, we're looking for moles. Sorry, I got kind of confused there. We don't know moles. This is what we're looking for. We know R, that's the constant, and we know the temperature. So we're going to be solving for N in this equation. So that means we're going to have to rearrange this equation. Okay, PV equals N R T. All right, we want N by itself. So we can get rid of R2, R and T by dividing both sides by R and T. Okay, then these cancel. It'll be N is equal to P times V over R times T. So let's plug in our numbers. So P is 101 kilopascals, and V is 0.351 liters divided by R, again, is up here, 8.31. It's always going to be 8.31. It's the constant. I'm not going to write out this big, huge unit. So 8.31, and T is 297 Kelvin. Again, it's really important that you have these in the correct units. All right, they must be in kilopascals, liters, Kelvin, and moles. So keep that in mind. All right, so to calculate this, we're going to take 101 times 0.351 divided by 8.31 times 297 equals 0.0144 moles. And I know the unit because we were solving for moles. So here's our answer. Okay, that's how many moles of gas are present. So that's how you use the ideal gas law. We'll be doing more. We're going to actually be doing a lab next time on this. You'll get to use this equation more. All right, we'll see you in class.